In this section, we're going to talk about improper integration, which deals with two types of integration related to infinite behavior of a function. So let's just remember for a second our definition of the definite integral. So going back to our original definition, just what is the definite integral? The definite integral says that given a function, little f of x, where capital F of x is the general antiderivative of f of x, then the definite integral from a to b of f of x dx equals that antiderivative, capital F of x, evaluated from a to b, which of course would just be f of b minus f of a. We've been using this definition for weeks and weeks and weeks, actually 2 semesters, because we used it back in Calc 1 as well. But it was specific, and this is the part we're going to get into today. It did say where a to b is a closed interval, and f of x, little f of x, did not have any infinite discontinuities on that closed interval from a to b. So what happens if one of those two conditions is not met? And that's what we're going to talk about in this section. And it's actually not going to be too bad. What we're going to do is we're going to combine what we know about limits at infinity, or limits as we have infinite behavior. So going back and utilizing some of our limit tools and techniques from Calc 1. And of course, practicing all of our integration techniques that we've been working on in this chapter. So what we're going to do is we are going to extend the definition of the definite integral to include, whoops, sorry, I scooched that down right there. So we are going to extend our definition of the definite integral, and let me find my mouse here, extend the definition of the definite integral. And what we're going to do is now we're going to include infinite intervals. So from, say, a closed endpoint A to positive infinity, or from negative infinity to a closed endpoint A. And we're going to talk about functions that have infinite discontinuities on a closed interval from A to B. So something like the function f of x equals 1 over x minus 1, that has a vertical asymptote at 1. So if we were to be integrating that from 0 to 2, we'd have to, of course, consider what happens at that point, that kind of strange infinite behavior. What would that mean if we wanted to integrate it across that vertical asymptote? Okay, so what happens is we break down what we call improper integrals, because they don't fit that standard definition where we have a closed interval and we do not have any infinite discontinuities. If one of those two things happens, we consider these improper integrals, and we have 2 of them. Type 1 is an improper integral on an infinite bound. So I grabbed this little function right here, and if you notice here, if we were integrating from a to infinity, that would be what we call a type 1 improper integral. So if we integrated from a to infinity of f of x dx, if it has an infinite bound, then we call that a type 1 improper integral. Now, if the function, as I've drawn it here, if the function happens to be greater than or equal to 0 above the x-axis, we can literally be thinking of that integral, just kind of going back to a previous definition about areas between curves and the x-axis. We could be thinking about that integral representing that area under the curve to the x-axis. But this is that's a type 1 improper integral. Now, on the other hand, a type 2 is if we have an infinite discontinuity. So in this case, let's say we wanted to integrate this function from a to 5, called it just some generic a there. If we're integrating from a to 5 of this function, let's call it g of x on this guy, since I called the other one f of x. If I said the integral from a to 5 of g of x dx, because there is an infinite discontinuity at a, we would call that, or a vertical asymptote, we would call that a type 2, because there's an infinite discontinuity, or a vertical asymptote at x equals a. And so we'd have to think about, what does that mean? How do I do that? And the process for doing that is actually fairly simple. What we're going to do is we're going to replace the issue on the bound, right? Whether it's going to infinity or an infinite discontinuity, we're going to replace that issue on the bound with a variable t. And then we're going to let the limit of t approach whatever it is, approach a or approach infinity. So let's take a look at a couple of examples, but those are generically our 2 types of improper integrals. So let's take a look at a specific one. Let's look at something like this. Suppose I had the integral from 1 to infinity of 1 over x dx, and I graph that over here. So if I wanted to find that integral, graphically, what I'm thinking about is what is this area under the curve from 1 to infinity? So there's like, that means that there's no upper bound. It just keeps going on and on and on and on forever. So how would I do that? Well, one way to think of it is to actually think about cutting that off at some generic value t. And so I could say, well, what if I consider the integral from 1 to t of 1 over x dx? But then I want t to keep going, so I have to also add in the limit as t goes to infinity. And I have to think about what's going to happen there. So this becomes a two-part problem. First, I figure out what's the generic limit from 1 to t, and then I let t go to infinity. So as mentioned before, we're going to use our two strategies from Calc 1, limits, and from Calc 2, integration. So we're going to be using both integration and limit tools to get these improper integrals, to figure out if these improper integrals have a value or not. So let's go for it. So here we're going to integrate first. So let's integrate first and see what happens. So when I integrate this, I still have the limit. I'm not going to do the limit. That's going to be my second part. So I still have the limit. I will carry it along, the limit, as t approaches infinity. And I need to integrate the integral from 1 to t. I need to integrate x to the negative 1, or 1 over x. Well, what is that? Let's erase that and actually just do it. What is the integral of 1 over x? Well, that's the natural log of x, but we're evaluating it from 1 to t. So we keep going. I'm not taking the limit yet. Right? I'm still just evaluating the integral. It's a definite integral. I'm evaluated across the bounds. So that's the natural log of t minus the natural log of 1. Now I've evaluated the integral, but I'm going to keep simplifying because the natural log of 1 is 0. So I end up with the limit as t approaches infinity of the natural log of t. What I've done right here is I've actually created a function. Let's just think of it like a of t. I've created a function. It's almost like I've created this function from 1 to t in this particular case because 1 over x was positive. It actually represents the area under this curve from 1 up to wherever that t value was, right? If I had stopped it at 2, it would be from 1 to 2. If I had stopped it at 5, it would have been from 1 to 5. If I had stopped it at 5,000, it would have been the area under the curve 1 over x from 1 to 5,000. And so that's what we've done right here. And whatever that t value is, it turns out it works into just this function, right? The area up to t from 1 under the curve 1 over x is just the natural log of t. Now what I'm doing is I'm thinking about, well, what is the limit? As I let that value t approach infinity, well, it's the limit of this function natural log of t as t goes to infinity, but that's infinity. That approaches infinity. The natural log is, as we approach infinity, is infinity. It is infinite. And so we integrate first, and then we take the limit second, and we see if that limit exists. See if it exists. If it is finite. Now, it is interesting to also capture if there's a couple ways the limit cannot exist. It could be doesn't exist because it's oscillating or something like that. But in this case, it doesn't exist because it is infinite. It has an infinite limit, this amount of area under this curve. And again, I keep referencing that idea of area because for this curve, since we're above the x-axis, that curve is always positive from 1 to infinity. Since we're above the x-axis, we can literally think of it as the area from the function to the x-axis. And it turns out that it's infinite. So if it is infinite, what we actually say here, and I will define all of these in just a second, we will say that this is a divergent integral. If we don't get a finite value, then we say that it is a divergent integral, right? That this is diverging. And we can see it right there, that, if we want to think in that area idea, what ends up happening under this function as we continue our t heading towards infinity, we let t continue to march on towards infinity, we continue to add area, add area, add area in such a way that the overall area becomes infinite. Well, would that be the same if we change the power? So instead of 1 over x, what if it was 1 over x squared? What would that look like? That's also an improper integral. has kind of a similar graph, except for it's always positive on the previous one, and I won't switch back. But on the previous one, this arm was actually down here because it was 1 over x, not 1 over x squared. This also will have just kind of a slightly sharper rate of change. It will go down just a little bit faster right here and go up a little bit faster over here. There's some things to notice if you wanted to compare this exact function to the one before. But we're still doing the same sort of thing. If we wanted to know what is the area essentially under this curve from 1 to infinity, what we're going to do is exactly like we did on the previous one. We're going to add in some generic t, and we're going to say, you know what is the integral from 1 to t of 1 over x squared dx? And then we're going to take the limit as t is approaching infinity. So we're going to find the integral first, and then we're going to take the limit of the result. We're going to apply those two skills here to compute this integral. So we're going to say, I guess I'll write it out. We're going to integrate first, limit second. So we're going to take the limit as t approaches infinity. Now we want to integrate this 1 over x squared. Now remember, 1 over x squared is the same as x to the negative second. So when I integrate that, I'm going to get negative x to the negative first. And we're evaluating that from 1 to t. Now we're still taking the limit. I'm just going to simplify a little bit and then plug in my bounds. This is going to be negative 1 over x, and then we're evaluating that from 1 to t. I'm going to keep going. That's the limit as t approaches infinity. I'm going to evaluate that across the bounds. Notice I'm not taking the limit at all until I get to the end. That's the second step of improper integration. So we've got to integrate first. So we've got minus 1 over t minus a negative 1 over 1, which of course is just 1. I'm going to write it one more time before I take the limit, just because I got some double negatives and whatnot going on there. So that becomes 1 minus 1 over t. Now we're going to take the limit. So we take the limit second. So now we take the limit. So we take the limit now as that t is approaching infinity. Well, as t approaches infinity, 1 over t is actually going to go to 0. So we're going to get 1 minus 0, which is 1. And that is the value of this integral. And it's really kind of an interesting concept, because what we have here is, again, a function from 1 to infinity that is above the x-axis. So that means that that integral that we're looking at is representative of the area under the curve, 1 over x squared, from 1 to infinity. And we just showed that that value is 1. It has a finite amount of area. That is a finite number. That curve is capturing 1 unit squared of area from 1 to infinity. And what we do here is we say that this is a convergent integral. We actually classify these as divergent or convergent based on if that limit exists or does not exist, meaning it is infinite or doesn't exist for some other reason. So that's how we're going to deal with improper integrals, and those are two fairly simple improper integrals, but they lead us into kind of a nice result that we'll wrap up this video with, which is, for what values on this power right here do these particular types of integrals converge? So we'll do that proof after I show you the definitions. Okay, so here is our official definition of improper integrals type 1. So this is when we're on an infinite integral, so our bounds in the integration are have an infinity, either positive or negative infinity. So if the integral from a to t of f of x exists for all values of t greater than or equal to a. So I have the little picture I drew over here. So from a to infinity, so in this case, because the function I just happened to draw is above the x-axis, this is the total area from the function to the x-axis that we're looking at right there. If that integral exists for all values of real numbers from t greater than or equal to a, then the integral from a to infinity of f of x dx is equal to the limit. As t approaches infinity, we replace that upper bound, that infinite bound, with t, and we take the limit as t approaches infinity. And the integral will be equal to that limit when that limit exists. If, on the other hand, we were going the other direction, so in this case I just drew one, and this one I dipped above and below the x-axis, so this would be a net area we'd be looking at here. I can squeeze that into my little picture right there. But the second part is if we happen to be going from negative infinity, this should be a negative infinity right there. I just realized I have that typo. This should be negative infinity to b. So if the integral from t to b of f of x dx exists for all real numbers where t is, in this case, less than b, because we're coming from the left side of the interval, so coming from negative infinity to b, f of x dx will be equal to the limit as t is approaching negative infinity. We replace that lower bound where we had a negative infinity, we replace it with a t, and the integral from t to b of f of x dx as t is approaching negative infinity will be equal to the integral from negative infinity to b of f of x dx when that limit exists. So again, thinking about when those limits exist, if the limit exists, then we will have a value for the integral, and we will call the integral convergent. On the other hand, if those limits do not exist, we call the integral divergent. Now, one last piece. If we had a graph, and I'm going to draw a graph. If we happen to have a graph and we wanted to integrate the function all the way from negative infinity to positive infinity, let's take like a little bell curved graph right here. Call this f of x, and say we wanted to integrate from negative infinity to infinity of f of x dx. If we wanted to find that integral where both of the bounds were infinite, what we can actually do is we can split it up into two pieces. We just find a breakpoint on the curve I drew. At kind of a natural breakpoint would probably be 0, but you can break it anywhere. And look at each of those individual integrals from negative infinity to a, if that limit exists, and the integral from a to infinity of f of x dx. If both of those exist, then we can find each of those, and then the integral from negative infinity to infinity will be equal to the sum. And so visually what we would be doing right there, if we happen to split it at 0, we would look at each of these and see if that limit exists, and then we could add them together to find the integral from negative infinity to infinity. So those are our definitions, and that's how we're going to work it. So anytime we have an integral type 1, we're going to replace the infinite bound with a t and take the limit as t is approaching either infinity or negative infinity. Okay, to wrap up this section on Intro to Improper Integrals, I wanted to do a little proof about powers on 1 over x to a power r, p, or something. And so if we were taking an integral from 1 to infinity of 1 over x, which we have here on the board, we were able to show that that was divergent, that integral went to infinity, whereas the integral of 1 over infinity of 1 over x squared, add a square on the x, and that integral converged to 1. So for what powers does it converge? Because we just showed that for 1 over x to the first power, we got divergence, but 1 over x to the second power, and we got convergence. So for what powers, let's call them p for powers, for what powers of p does the integral from 1 over infinity x to the p converge or diverge? So I don't have to go through the integration and the limit process every time I come across one of those, because these particular integrals can be useful when we're comparing to other functions. So sometimes we use comparison to determine if we're going to converge or diverge. That'll be a nice, easy one to compare. If we could compare to 1 over x to the p and easily determine by what that power p is if it converges or diverges. Okay, well, we have already shown that if p equals 1, that we're definitely going to have divergence. That was our very first example. So let's start off by saying this. Let's say given any power p where p is not equal, I was going to put it in parentheses, but I'm going to put a comma, where p is not equal to 1. And in parentheses, I will say we already proved that case. That case was already proven. So if it is not equal to 1, then the integral from 1 to infinity of 1 over x to the p dx is going to be equal to, remember, anytime we have an improper integral with an infinite bound, what we're going to do is we're going to replace that bound with t, and then we're going to take the limit as t is approaching infinity. We let t approach infinity, but in the integral we replace the bound with t. And that's going to be 1 over x to the p dx. And because we're going to integrate this, I'm going to go ahead and rewrite that power as x to the negative p power, so I can integrate easily with the power rule. So this is the limit as t goes to infinity. Remember, I won't write out this step again, but we always do the integral first, and then we take the limit. So this is negative p dx. So we're working on figuring out the integral, carrying the limit throughout my work as I go. Now the integral of x to the negative p, because p is just a power, so I'm going to go ahead and use my power rule here, x to the negative p. We add 1 and we divide by that same quantity, negative p plus 1. Now that's the integral, but I need to evaluate it across the bounds from 1 to t. So now I'm going to evaluate it across the bounds, take the limit as t is going to infinity. When I evaluate it, I get t to the negative p plus 1 over negative p plus 1. And then I'm subtracting, when I plug in 1, I get 1 over negative p plus 1. And there we go. Now I'm actually going to just keep going, simplifying a little bit. Here I'm going to go ahead and pull out the 1 over, there's a common factor in both of these terms of 1 over negative p plus 1, so I'm going to pull that out. I have not taken the limit, and I'm not going to until I get it simplified just a little bit. And so I'm going to pull out a 1 over negative p. Now, when I pull out a negative p plus 1, I'm actually just going to rewrite it. Instead of negative p plus 1, let's write it as 1 minus p. So I pull that out from each of those, which leaves me with a t to the other thing I'm going to do right here is, I don't really like it like that. I'm going to write that as negative quantity p minus 1. So I'm going to rewrite the power on t as negative quantity p minus 1. I'm going to do that because I want to drop that t down to the denominator for taking the limit. And here, since I factored that whole thing out, I just get minus 1 over 1. So I get just minus 1. Okay, keep simplifying just one last step, and then we can take the limit. So as t is approaching infinity, I have this, by the way, remember p is just a constant. So 1 over 1 minus p is just a number, and then I'm multiplying that by 1 over, now I'm going to drop the p, because it's a negative exponent, I'm going to drop it. I'll put that in red. I'm going to drop it down, and it's going to become a positive power p minus 1. It's going to change from a negative quantity p minus 1 to a positive quantity p minus 1, and we are subtracting 1. Okay, I'm going to keep going now because now I've got it, and that was a little bit strategic. I wanted it in that nice form. That's going to be an easy form to take the limit as t approaches infinity, but it is going to depend on whether p is greater than 1. Look at that power right there. When I take this limit, it's going to depend on whether p is greater than 1 or less than 1. And again, we were saying at the beginning that p was not equal to 1 because we already proved that that case diverged. We showed that that went to infinity in our very first example in this video. So here, I'm going to look at the other two possibilities, that we are either greater than 1 or less than 1. We get two different limits depending on that. So let's call it case 1. If p is greater than 1. So if p is greater than 1, then this limit as t approaches infinity of 1 over 1 minus p, 1 over t to the p minus 1 is going to approach, let's think about that. So as t is going to infinity, so we've got infinity down here, but p is greater than 1. So the power on this infinity is going to be positive. It's going to be infinity to a positive power right there because p is greater than 1. So 1 divided by infinity, or infinity to a power, positive power, is going to approach 0. So that's going to approach 0, and this is going to become, when we take the limit, 1 over 1 minus p times simply 0 minus 1, which is a negative 1, and that becomes 1 over p minus 1. Again, p is just a constant number. It was a power greater than 1. So this is a finite number, which tells me that I get convergence. Converges. Convergence. So we get convergence to this value. Well, what happens in the other case? So what happens if p is less than 1. So if p is less than 1, what happens? If that power on the x value is less than 1, well, then the limit as t is approaching infinity of 1 over 1 minus p times 1 over t to the p minus 1 minus 1. Well, think about what happens right there. If we are plugging in infinity here and p is less than 1, this is infinity, this is going to be to a negative number. Well, when we have a negative number in the denominator, that's going to pop up. That's going to become infinite. So this is going to become 1 over 1 minus p times infinity minus 1. Well, infinity minus 1, of course, is one of the infinities. Whether it's positive or negative is going to depend, I guess, on where we are there. But it is infinite, so this is divergent. So if p is less than 1, we're definitely getting infinite behavior and we're getting divergence. Okay, so we can summarize now. The third case, of course, is if p equals 1, but we already proved. Now let's write that up. Case 3. P equals 1. We had already shown that that was divergence. Divergence. Diverges. And that was example number 1. We had shown that. I'll scooch. There's a lot to get on the screen. There it is, right up there. Example number 1, if p was actually equal to 1. Remember when we took the limit there, that was that special case. We couldn't apply the power rule there. When we integrated, it became the natural log of x. So what we can do is we can actually summarize those 3 cases down to one nice little piecewise description. We can say the integral from 1 to infinity of 1 over x to the p dx is going to be equal to, and we're going to write it like this. A piecewise function, because we have 2 scenarios, we're going to say this. We're going to say that this converges to 1 over whatever p minus 1 is if p is greater than 1, and that it diverges otherwise. It diverges if p is less than or equal to 1, summarizing case 2 and 3 together. And that is a useful result. Anytime we come across an integral that is of that form from 1 to infinity of 1 over x to the p, we will know simply by what the power on p is, or what the power p is equal to, and how it compares to 1. If it is greater than or equal, if it is greater than 1 or less than or equal to 1, whether we converge or diverge. And so that does give us a nice little summary for that very specific type of integral. Okay, just to wrap up improper integrals type 1, our official definitions here and our steps. Basically, if we have an infinite bound on our integral, if one of our bounds in the definite integral from a to b is infinite, either positive or negative infinity, we recognize that it is an improper integral. It's type 1. We're going to replace that infinite bound with t. We're going to integrate, take the limit as t is approaching either infinity or negative infinity, and determine the convergence or divergence. If both of the bounds are infinite, we're just going to split the integral up and look at each of the 2 integrals individually to see if we can show that they are both convergent. If so, we can add them up, and that will be the value of our integral. All right, on the next video, we will work with some of our integration strategies in conjunction with these improper integrals.